Welcome back to our lecture Machine Learning, and in this video we want to talk about decision trees. So in the last video we have seen KNN classifiers or regressors, and I already mentioned like a concept like lazy learners, right? Where the model in the KNN actually is not really doing some learning, right? Or the learning is only done during the time when the new instance arrives. And here we want to talk about a different concept now, where we specifically see what actually training, what actually learning means, because I motivated in the intro video that machine learning more or less tries to automatically learn rules from the data, which we didn't really see in a KNN classifier, right? And here in this decision tree lecture, we will specifically see some very intuitive way of how to find and how to represent these kind of rules. And the motivation for this is that we can more or less like do some kind of classification by playing a game where we're asking questions and getting answers. So some of you might have heard about this 20 question game, where you have, for example, 20 questions available to figure out which kind of animal is someone thinking about. Okay, so you can, for example, start asking like, does it have fur? What you are thinking about. Could be then yes. Does it bark? Could be yes. And this list continues until you have reached the maximum of 20 questions, or you know the answer, for example, dog, right? And then, of course, if I ask someone else, right, who thinks about like a specific animal, I can again ask, does it have fur? And you say no. Does it fly? And you say yes. And then I might say bird, okay? So you see, by asking these questions and following these answers, I can, at the end of the day, find a final answer. And this is what I'm predicting, what you are, so to say, thinking about. Okay. And indeed, this is more or less the core idea of a decision tree, because these questions, they relate to the features of the instances, right? The animal has fur, it can fly, it barks. So yes or no always, right? So these here are asking questions to the features, to the input X, so to say. And here, this is our prediction, our predicted Y, the class label. Okay, so here a bit more abstract now. So let's say you have a specific data set. So here, this is our X, right? So every row corresponds to one instance, Xi, for example, here. And this here is our Y, our targets. We are still in this supervised learning scenario where we have training data corresponding to the input features and the given target label. Okay. So here in this case, again, we have a four-dimensional data set, four-dimensional feature vectors, and we have, of course, this class label like discrete yes or no setting. And here the task is, for example, to make a prediction model, to learn a machine learning model, which says based on the temperature outside, the humidity, the wind speed, do we want to or should we play tennis, yes or no? And here you can now play similar to this 20 question game now, like this game, right? You can ask, for example, how is the weather outside? Is it sunny? Yes or no? Is the temperature hot? Yes or no, for example. Okay. So here we can see it in this simple example. So the first question could be, for example, how is the outlook? So what is the outlook? And here we have three answers, not just yes and no. So we have sunny, overcast and rainy. So sunny, overcast and rainy. And what we see is, for example, here in the overcast setting, which is here, 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 and here, the answer in the training data was always yes. Okay, so which means if we now, for example, also get a new instance already, so like a new test sample, which has an outlook which says it's overcast, then it would be a good idea to already say yes. Okay, because here all the training instances also had a yes already. Okay. So we have essentially asked the first question in our 20 question game, and now we can just recursively continue. So for example, we can look at the sunny branch, right? The sunny branch would be like here, these instances, and this one here. And recursively can now ask a question. So for example, we could ask, let me see whether we have this example. Yes, we could ask for the humidity, for example. Okay, so this could be our second question, so to say. We ask for humidity. The answer could be normal or high. And then again, we can make our final decision, yes or no. So let's go back here. So for example, sunny, humidity high, here it was no. Humidity high, the answer was no. Humidity normal, the answer was yes. Humidity normal, the answer was yes. So normal is yes and high is no. And we can do the same for the wind, right? We can ask here, so if the first answer was rainy, we can ask now a different question, right? We can ask for the wind speed, whether it's strong or weak, and then again we can make the final decision. Okay? So you see that this classification decision we can make now corresponds a bit to this question-answer game, right? We're recursively partitioning, so to say, our space based on the answers we have obtained so far and asking many, many questions. At some point, we can make our final decision, which is it's aligned and matched with our training data. And then, of course, the hope is now, since it matches training data, it will also generalize to unseen new test data. This is, by the way, in general, one assumption, let's say at least classic machine learning models, that if it works well on the given training or validation data, we hope that it will also generalize to the unseen test or really new data. Okay, and here it's the same. And this here is more or less like already the concept of a decision tree. You see that we have here like questions or tests, which are usually testing against the different features, right? So here Outlook was a feature, and then we have here the answer. So what was the feature value? And then we either continue with another test on potentially a different feature, or we have a final answer, which is the leaf node of this decision tree. So here the leaves are always the answers, and the inner nodes are questions or tests. So the other example we have seen so far was for discrete features, right? Of course, the class level was always discrete, it's classification, but also the features were discrete. So what do we do if we have continuous features, so numerical features, like in our example before? So recall, this was exactly the same example, or is exactly the same example as in the KNN classifier, right? Remember, here was a bit like a green region, here was this blue region. And how do we do now a decision tree on such kind of data? We again have to ask questions. We have to do a test. And usually what we are doing are so-called binary splits, which are tests in the form of asking whether a feature or whether the value of the feature is below or above a specific value. Okay, so for example, we could ask, is the feature x2 smaller than or equal to 3, which would correspond to splitting along this axis in this diagram, right? So we are partitioning the space as before. We have essentially our full training data, and by asking a question, we can split it in different partitions, in different subsets. And by asking x smaller or equal to 3, we get on one hand this region. So here x2 is smaller than 3, so it's a true. And for these instances here, x2 is larger than 3, so we're in this branch, okay? And then similar to this categorical discrete case, we can continue. So for example, for this answer, right, which corresponds to the lower subset, right, the lower part here, we can ask again, for example, x2 smaller than 1.7, which would be here, right? So again, we subdivide it into regions. So here the answer is yes in this lower part, which would be this branch. Or we look at this part here, which would be this branch, okay? And for the other branch, which we had here, where the answer was false, where we're in the upper part, we can, of course, now do a completely different second question. So here we could, for example, ask x1 is smaller than 7.8, yes or no, which would be like splitting here, right? You see it in this part. So we had originally this upper part, and now we split it further along this direction, along the x1 direction, okay? So the hope is, and this is, I guess, not surprising to you, is that we want to find here the regions which are somehow like clean, right? You see here, this region now already is rather bluish mainly, right? So which would correspond to this branch, right? x2 larger than 3, x1 smaller than 7.8. So here, this region. And you see it's mainly blue, right? 112 blue instances and a couple of other instances, red and green, okay? Or similar, if we, for example, look at this branch, larger than 3, so it's up, larger than 7.8, so it's here. And then, for example, we can split one more time, x2, let's say, larger than 3.9, which is where? Here, apparently. this is this branch, right? Yes, here. Right, okay, we have 3 splits, right? 1, 2, 3 splits. So 1 split, 2 splits, 3 splits, right? So this is this region here, and you see it's mainly green. Okay, so this would be our desired goal, so to say, to find these nice clean regions, because now we can essentially stop, right? So once we have here reached this region, and then we more or less can say, okay, everything which is in this region is blue because blue already dominates this region anyways, right? Or probabilistically speaking, right, if you look now at this from a probabilistic point of view, the probability that some instance which falls into this region is blue is very high, right? It's 112 divided by the overall number because we have such a large fraction of blue, okay? So again, as before, the questions are tests to the features, and now in the case of smaller or larger than some number, the answer then is true or false, right, at either smaller or larger. And at the leaf nodes, we have our final decision, which is technically speaking a distribution over these classes. Okay, so red, green, and blue, and we see here high probability for class blue and low probability for the other classes, corresponding to the counts of these objects in these regions. Okay, and that's essentially really all how a decision tree looks like. Here it's again just what I already said now a couple of times. We have the nodes, which are these tests. We have the branches, which are, so to say, the answer, the outcome of this test. And then we have the leaves, which are specific regions and where we have according distributions, according to the training instances in this region, which correspond to our final prediction later on we want to make, right? So here, most likely red, here, most likely green. So that's a decision tree. So how do we then do inference on a decision tree? And now you learn a different term here. Inference means we get a new instance and we want to make a prediction for this instance. This is known as the inference step in machine learning. There's also like the training or the learning step, which cares about how to construct such a tree. We haven't talked about the learning yet, right? I just here have shown to you some final result. We'll talk about this later in more detail, but you should remember these 2 steps. Learning or training is finding this kind of model, right? It's a model. It's like a representation of your knowledge, so to say. That's a training/learning. And then there's the inference phase, which cares about classifying a new sample. Okay. And the inference phase for decision tree is actually, as you can see here, extremely simple. We already said it a couple of times. It essentially just takes this new attribute of the instances attributes, and it's asking these questions, right, following the trees until it reaches one final region, right? So we find the region that contains this instance by following these pairs, and then in this region we just look at this probability distribution. So here it's again technically written. This simply means we see in this specific region where we are landing in how many instances do we have of class blue, red, or green. This gives us, again, this probabilistic point of view we have seen already for the KNN classifier. And then usually we do the argmax, okay? So as before, we actually don't have to do this normalization. We can just look at the counts, okay? So this is how inference works, extremely straightforward. And what you also see is that this is extremely fast. So in a KNN classifier, we have seen this problem that the inference step, so making a decision, is actually expensive. We have to traverse all data points. We have to see what are the nearest neighbors, and then we make the prediction. And we have to store all these instances, right? That's extremely expensive. Here in a decision tree, this is much faster, right? So let's say we have this example. We don't have to store the full data. We just have to store this model, meaning we have to store what kind of test do we do and what kind of final distribution in this region do we have. Okay, so we just have a very compact representation. That's one big advantage, only a small memory footprint. And the second advantage is, again, the actual inference time is very fast, because for classifying we don't have to scan all objects. We just have to answer 3 questions, 1, 2, 3, and then we are here and we can make our prediction. So this is a very, very big advantage of a decision tree. Okay, good. Then I guess we can actually skip this because I already said this. We can always have this probabilistic point of view. And here it's just, if you're not familiar with it, one more time. So we can represent these probability distributions in a discrete sense as like an histogram, right? So here if we have 4 classes, for example, we have here the 4 different probabilities per class, which should of course sum up to 1 and should be all non-negative, right? And you can think about like you have specific colors and specific occurrence counts, and then we just take here the ratio, so to say, right? For example, the probability of that a class, or meaning a ball is red, if you have such a region where you have 4 red, 10 green, and 6 blue ones, it's just 4 divided by the overall number. I guess you're all familiar with this anyways. But why do we do this? Because later on, we do not just have these simple categorical distributions, but we have a more advanced view on machine learning from a probabilistic point of view. Okay, good. Then, for the very last time, to make it clear to everyone, so if we want to make a final prediction, we just have to traverse the tree. So here it's illustrated with this black star, right? And you should all do this at home one more time. So what is the way we have to follow in this tree? So what do we do? X2, for example, for this one is here, right? X1 is somewhere here. So x2 is larger than 3 apparently, so we have to go here. Then we have a question regarding x1. Is it smaller than 7.8? No, it's larger. So we go here. Then another question on x2. x2 is 6. So it's smaller than 3.9, so we go here, right? So the final path we are following is here, here, and here. And then we see here in this region, we have this probability distribution, unnormalized so far. So we have 4 divided by 5, 0 divided by 5, 1 divided by 5, right? So this probability distribution is then what we use in this region. 4 divided by 5, of course. 0 divided by 5, 1 divided by 5. So the majority vote would go here, of course. We predict it as red. Okay? So what you see is that the decision tree, using these so-called binary splits, is subdividing our space in these rectangular regions. Okay, so in this KNN classification, we have seen this kind of Voronoi cancellation for 1 and n, or some more complex shape for KNN in general. But here we're always getting this kind of rectangular shape region, which is the result of these binary splits. And since we always just split on one attribute. So indeed, this is often a question which I'm getting in a live lecture here is, of course, in general, we can do here more complex stuff, right? We don't have to just restrict ourselves to binary splits, asking is it smaller or larger than 3, but we could think about like doing like questions on all features at the same time. So x2 smaller than 3 and x1 larger than 7 and x15 between 5 and 20. So you can, of course, in principle, ask many different questions here, and you will always get an answer, of course. But the point is, the more complex the questions are, the harder it is to find a good tree. So later on, we will see how we construct usually such decision trees. And that's the hard part, right? The learning is the hard part here, how to find this tree. And if you have very complex questions here, the learning will be even more expensive. So usually for continuous features, we look at these binary splits only. Okay. Oh, by the way, here's the actual feature. I didn't see this even. So it's 8.5 here and 3.5 apparently here. Good. So then let's continue with the construction. As I said, that's the hard part. The inference is easy. The classification of new samples is easy, but how do we find such a tree? And for this, one more time, recall what we have to do is, and we want to first split our actual given labeled data into 3 subsets, the training, the validation, and the test. And the naive idea would be build a tree from the training set, right? So this is why it's called the training set. We are training on this kind of data. And then we can use our validation set, right, on this constructed tree to make predictions, right? So we are building a decision tree on the training set. We are using our validation set to do predictions with this tree. And then we can compare the predicted label with the true labels. And then we can try to find the best tree, right? And this best tree we found, we can then finally evaluate on the test set. Okay, that's a general principle. And you see already potentially a problem. So how do we actually do this? How do we pick the tree that has the best performance on the validation set? So the naive idea is that we simply enumerate all possible trees, right? So like in KNN, where we pick k equal to 1, 2, 3, 4, 5, right? We enumerated all the different k's. We can now think about we're enumerating all possible trees, right? So all possible trees, and then we just see which one performs the best on the validation set. Is that a good idea? I guess we all agree that this is not a good idea, right? Because there are far too many trees we could potentially enumerate. So think about a simple setting, right? Like here we have 1, 2, 3, 4, 5, 6, 7, 8 data points. Okay, we have 8 data points. We can have already 8 different splits here if we restrict ourselves to binary splits. Like we could split here, we could split here, 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 or here, right? So we can, actually here it doesn't make sense to split and here it doesn't make sense to split, right? Because we wouldn't gain anything. So actually we only have 8 minus 1, so 7 splits. So in the middle, here, 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 here. So these are the possible splits we have at the root node, right? Think about a decision tree, right? We have here the first question and then we do the split. So for the root node, we already have many different choices. Okay, and this is only for one feature. So let's say you even have 2 features, right? Then you have 2 times these choices. And of course, you only don't usually have just 8 points, but let's say you have 300 unique values per feature. So let's say 300 unique training samples, unique training samples. Then you would have 299 possible thresholds you can test times the number of features, which would be here in this simple, very tiny data set already 600. Okay. And this is only for the root node, right? So here's 600 choices. Then you have to continue, right? So here then you would, of course, you have separated then your data. So the data is slightly smaller, but still you would have potentially 300 choices here and here 300 choices, let's say, okay? And you see that this quickly blows up, right? Because this is like an exponential growth, like it's 600 times 300 times 300 choices, for example, right? So it's a very big space. And of course, you don't just have 2 questions. You might have a very deep tree. So long story short, enumerating all possible trees is not doable at all, right? So we can't do this naive solution. So indeed, there are some theoretical results on this. We don't discuss it in detail, but it's not only just very expensive to enumerate these, but you can show, for example, that finding the optimal tree is NP-complete, hard or complete problem. So what does it actually mean, right? Because NP-completeness relates to decision problems, if you recall from theoretical computer science. So it's like relating to a problem where the answer is yes or no. And here, for example, it relates to the question whether we need a specific number of tests to make a prediction, for example, or minimizing the number of tests. Or you can answer even other questions, so like even identifying what is picking the root node or identifying a good root node. This strategy is also an NP-hard problem, or the optimization version of its. So the decision version of the optimization problem is an NP-hard problem, so to say. So long story short, this doesn't work. It's too hard to do this. So instead, what is done in practice is essentially almost exclusively like a greedy approach, a top-down approach. Top-down approach meaning at every time point, we make locally the best decision. Put differently, in this example, we start with the full data set, and then we see, given this full data set, what is the single best decision I can do now? So what is the single best test I can do? So I'm getting, let's say here, this split into regions. So what is the outcome with these 2 regions? Do they look good or not? And looking good means, are they somehow clean or not? And among this single local decision, I pick the best one. And then I just recursively continue. Okay, so I first decide what is here, greedily, locally. Once I've decided, I just recursively apply this to the corresponding subsets. Okay, it's just some recursive approach. We're always taking one subset of the data, making a decision, split it, and then continue. Okay, so this is usually how decision trees are built, using a greedy top-down approach. Okay, so in a bit more detail. So what we need potentially is some way, again, of evaluating how good such a split is, right? So because we want to do it in a greedy fashion, we have to see if this split a good idea or this split a good idea. And so let's look at an example again. So let's say here's our training set. It's a full data set. Let's say here's all red, here's blue, and here's all green. And then we could see what is a good split. So for example, we can think about splitting here. Might not be such a good idea, right? Because then this side is very clean, right? Here we could say, yeah, it's very likely red. But if you split here, right, this region would be very, very impure, right? Still mixed. So we can't really make a clear decision, okay? So it might be better, for example, then to split here, right? Because then the left-hand side is completely red. Perfect. We are very happy. We can make our prediction already. And the right-hand side only contains two classes, right? So the red class is gone. So this seems to be also very good, good shots, right? So this split might be quite good. Similar, one could argue, for example, that this split is somehow decent, potentially not, right? Because here it's still mixed and here it's still mixed. But for sure, such a split is not really good. And this split is even worse, right? So you see, but different splits lead to different local, also different performance, so to say. And we want to pick a good one among these. So what do we need? Similar to like evaluation metrics for classification, we need some measure to make this formal, right? And one way of doing it is a so-called misclassification rate. So here you see the formal definition. So the misclassification rate simply means we want to, first of all, we have to define like the error first of all. So what is the error at a node? So let's say we have here the probability of a class, right? Here we look at the largest probability. Okay, this is what we have seen, for example, before in the KNN. So let's make it more clear. Let's say we split here, right? We split at this line. Then here on the right-hand side, we have probabilities of 150 divided by 150, 0 divided by 150, and 0 divided by 50, because the other cases are gone. And here we would have 0, 150 for red, right? Red is gone. 100 times 150 for blue, and 50 times 150 for green, right? So the misclassification rate in this branch would be 0. We can say everyone is red. How do we compute it formally? We take just the largest probability, right? Which is here 1. 1 minus 1, so 0 error. Here in this case, what is the largest probability? It's 100 by 150 to 2/3, which would be this term here. 1 minus this 2/3 is 1/3, so the rest, so to say, and the rest is misclassified. If we would stop, right? If we would have to make a decision for this subregion, we would say blue, because it's the largest one, and then this would be misclassified, okay? And this is what this term is measuring. It's essentially measuring how much in this subregion would be misclassified if we would have to make now a decision, okay? So here it would be blue, so this is all misclassified. And now, how do we decide on a split? We decide on a split by picking the one which leads to the best improvement, so to say, in the misclassification rate. Improvement means the following. We compute the misclassification error in the current full set. So here for the full region, which apparently in this case is 0.5, right? In the full region, half of it would be misclassified. So we would classify it as red. All these would be misclassified. You see it also illustrated here one more time. And then we subtract the misclassification from the sub-roots, sub-child, so to say. Here we have a misclassification error of 0. Here we have this 1/3 error, right? So here would essentially be 0.5 minus this here, by the way, is the size of the corresponding left or right child. So this would be like 50% in our case. So 150 divided by 300. And here also 150 divided by 300. So these are the relative sizes of the left and right child, okay? Because it might not be equally sized, right? One might be smaller than the other one, okay? So we have to weight it accordingly. But here we are looking then at the corresponding misclassification error in the corresponding childs, okay? And of course, what we want is that this gain is very large. So if you, for example, have here a very high misclassification error, right? And let's say here it's perfectly clean and here it's perfectly clean as well, then this would be all 0. So this term would be then overall very large. Okay, so the gain in the misclassification error is large. That's here the delta. We want this gain to be as large as possible. Okay. And then again, in this example, it would turn out that this split is not such a good idea. Again, this is clean, but this is completely messy. While this split is quite good, as we see it's 0.5 minus 0 minus 50% of this, right? 50% of this term. leading to a quite large number. Okay. And then, as I already said, we do this then just recursively in a greedy-like fashion, right? So we start at the full data set, we figure out what is a good split, right? So this one or that one. Once we have decided, we fix it, we really subdivide it in these two children nodes here, right? And then we just recursively see, okay, for this subset, we check what is the best split and we subdivide. Here we check what is the best split and we subdivide, okay? Until we hopefully reach a state where it's getting more clean and clean and clean, right? So here, for example, it's mainly green, and here, for example, it's mainly red, or after splitting it becomes mainly red, and so on and so forth. Okay. Let me actually jump to some other slide deck, not slide deck, but slide, to make this clear already at this point. Indeed, how this works is somehow like, and at least in the expensive way, a very exhaustive search. Okay, so what I mean with this is the following. So let's say we have this data set here, okay, our full data set. And now I said we want to pick what is the split which leads to the best gain. Indeed, one way of doing this is in a quite exhaustive way, that we really split at every possible position and we measure what is the gain. Okay, here, for example, you see it again. So here's this delta, this gain. So how much do we improve in the misclassification error, for example, if we split feature x1 at a specific position? Okay, and then you see here, if we split here, it's not much of a gain. If we split here, it's much better, and so on and so forth. And we can do the same for the other feature. So if we split here, here, or here, we get a specific kind of gain values. Okay. And then finally, we pick the one which has the best performance. So in this case, we see this goes up until, let's say 0.04-ish. And here it goes up until 0.07. So here, this would be the best gain. So one would do, first of all, apparently this split here. Why? Because here, of course, it's already a very large blue region. And this is also somewhat good because blue has mainly disappeared from the lower part. Okay. So again, indeed, in the very expensive way, we do it now per feature testing all splits, and then picking the best. And once we have this, we do this recursively. Okay. Here already one other point. Of course, you don't have to do this really exhaustively for every possible split. You can think about, like, you look at your data range, let's say between 0 and 10, and then you test, let's say uniformly or based on some other heuristic, you test 100 different possible splits. So essentially you get some kind of downsampled version of this plot, right? Not all possible solutions, but just a few of them, right? So here, 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 and then you pick the best among these, okay? But this is indeed more or less how it works, that you really do this per feature and then picking the best one and then recursively continue. Okay. Okay, so this is what we have seen here for the misclassification rates, right? Here's again defined this gain, and here's again how this then looks like, repeatedly applied. And why I did this break or this jump to the other slide was, indeed, this misclassification rate is not the best measure. Okay, it's one measure we can think about, but as it turns out, it's not the one which is actually used later on in practice because it has some issues. And I show you here the two issues which this measure has, which then motivates us to use some other measures. So the first one is that this misclassification rate might be 0 or might not show any improvement, even though we get somehow like a better result, we get a more clear decision. Here's a simple example. So let's say we have this data set and we see that 40 out of 200 would be misclassified, right? So the misclassification error would be 40 divided by 200 because the majority vote here would be green. So all the red ones would be misclassified. But if we now, for example, do a split here or here, so we split either here or we split, for example, here, and we're calculating this gain in the misclassification rate, so you can do this at home, it would turn out the solutions for these sub nodes, so to say, would still be 400 divided by 20. So meaning if we subtract this from this one, the gain would be 0. Okay, so the delta would equal to 0 in this case. So the approach would not see any benefit in doing this. If the gain is 0, we shouldn't do the split, so we would essentially stop. Okay, so the approach would stop because there is no gain. Okay, but I guess we agree that splitting here would actually help, right? Because then the left-hand side would be perfectly clear and only the right-hand side is mixed. And then in the next step, we could split here and then we are done. Okay. But this is not really seen by the misclassification rate. It might stop too early because we have here somehow like a linear effects going on. That's one important point. We have a linear effects like, so we have only these ratios, right? Number divided by the overall number. And then we have here also here this linear term. So overall, this gain computation only has some kind of a linear effect on these decisions. So we don't see really that this is really already a very good result, right? Since this is quite bad, right? And it's actually even worse than what we had before, right? Because here only a bit of the full was misclassified. And here in this part, it's even worse. We don't see this, right? This gain here on the left-hand side is disappearing, right? It's disappearing because the right-hand side is so bad, okay? So this is one issue. And the second issue is somehow related, that we don't see really like a change in the corresponding class probabilities. What does it mean? So let's say, different example, before the split, we have a scenario of 50-50. 50% green, 50% red. So 400 green, 400 red. And now we split in one case in 100. So in this way, how you see it here on the slide, right? So here we have a bit more like still mixed regions, right? So 301, 301. Here it's one pure region and one still quite mixed region. You see again that this misclassification rate will be the same, okay? So we can't again distinguish between these two, right? It relates a bit to what I said here. So we can't really see that this very clean region already like it's very nice result, and this essentially then is done, right? We can stop here in this region in the subtree. We only have to focus on this one in the decision tree. This is somehow not reflected in the misclassification rate. The main reason again being that we have somehow like these linear effects going on, so to say. And that's indeed the reason why there are many other criterions how to pick it, which are trying to avoid this issue, so to say. So in general, what we're looking for now is we're looking for some criterion, I of t of this subtree of this subset of instances, which measures how pure this region is, right? Again, if the region is perfectly pure, we can stop more or less, right? It's all green, then we can make a decision. So we want to make sure that we get these pure regions. And indeed, there are a couple of requirements on this measure, actually very simple requirements. One is that this measure should be maximal if we have equally distributed nodes. Classes. So let's say we have a region and it's 3 blue and 3 green and 3 red, right? Then this measure should be maximum, so the highest impurity, so to say. The measure should be 0 if it's perfectly pure, so only red, and it should be a symmetric measure, meaning we don't want to, for example, that so 3 blue and 20 red should be the same as 20 blue and 3 red, right? Because we don't really want to distinguish between what labeling we have, so to say. We just care about the proportions, okay? So these are the criterion on this measure. Okay, so here's just an overview of these different measures then. We talk about this in more detail in a couple of minutes. So you see here the misclassification rate as we have learned it before. So these are the probabilities of the different classes inside a specific region. So let's say 80% red and 20% green, for example. And then misclassification rate is just calculating this term. And then we have the entropy and we have the Gini index as an alternative measure. So what I said before is that this misclassification rate is somehow like having a linear effect on this kind of on this measure, or it's measures in some linear way. And here you see what I meant with this. So let's say we look at the probability of class 1 in a specific region. So meaning here, for example, we have a region where class 1 has 0 probability, so it's 100% the other class. So here we have a region where we have 40% class 1. This is a region where we have 80% class 1. Here's a region which is perfectly pure, okay? So this is essentially the percentage of region of class 1 in the specific region, very pure region, also very pure region, completely mixed region, okay? And if we essentially vary the purity inside this region, we see that this misclassification rate behaves in a linear way, okay? So it increases and then it decreases, of course, again, right? Because here are the nice solutions. In contrast to this linear increase, the other two measures behave like this, right? Essentially, it's the same. One is just scaled a bit, but they have specifically here this steep increase at the beginning, then it's becoming more flat. So why is this helpful? That's the important point. Why are these measures better and why is this linear way very bad? So what this steeper increase tells you is the following. So if I have the choice between, let's say I have a clean region and a semi-clean region, right? So I would always prefer the more clean solution. Let me go back to this example. So here we have two semi-clean regions, pure regions, and here, however, we have a very clean one and a mixed one, okay? So what this steep increase tells you is if you have a clean region and you make it slightly less clean, right? This is punished a lot, right? Because we have here steep increase, right? From clean to or pure to less pure at the beginning, it's a very steep punishment. Remember, high numbers are bad, right? We want to have low numbers, okay? However, if the region anyway is already quite impure, right? It's already like 40% to 60%, then it doesn't matter too much if you make it 50-50, right? 40-60, 50-50, this is all roughly the same, right? This is all equally bad, right? However, going from a 100% clean to a 90% clean, this is punished a lot, okay? In contrast, again, this linear doesn't distinguish, right? In the linear case, going from 60-40 to 50-50, from here to here, is the same delta as going from perfectly clean to 10%, right? And this is why the other two measures are usually better. They prefer, so to say, the very pure, the very clean regions, because this is strongly penalized. The unclean regions, how they exactly look like doesn't matter too much, right? So this is rather flat, and here we have the steep increase. So we focus, so to say, on the purity more. And this is why the other two measures would prefer this here, because this gets a very, very low term. And this here, okay, it's not clean, but it doesn't matter whether it's like this or whether it's like this. No, they don't care too much, so to say, okay? So that's a big advantage, this nonlinear behavior in this measure. And now I quickly want to talk about these. I want to just explain what they measure. So the entropy, so some of you might have heard about entropy, specifically if you like a physics background, for example, or information theory background. So the Shannon entropy, to be specific, measures, from an information theoretic point of view, the number of bits you need to represent or to describe a distribution. Technically, it's like to transmit it through a channel. So what does it mean? Let's look at some example. So let's say you have a distribution which is completely flat, which is in our case the worst setting, right? We don't want to have a region in a decision tree where we have all classes equally distributed. Then we can't make any perfect decision. If you compute the entropy for this, and here's the definition of the entropy one more time, right? It will turn out that this becomes 2. So we compute the entropy with respect to the base 2, okay? So what is this 2? This 2 can be represented as the number of bits required to encode the information hidden in this region. So 2 bits, I guess you can all relate to this, right? So we can, for example, encode class 1 as 0, 0, the other one is 0, 1, then we have 1, 0 and 1, 1. So we need 2 bits to encode all these 4 different cases, okay? Assuming they are all equally distributed. If the distribution becomes more peaky, what you will see is that the entropy goes down, right? So here, for example, you have more likely class 1 and then the other classes are smaller. So the entropy goes down until to the extreme case, when the histogram is extremely peaky, the entropy becomes 0, okay? So this intuitively means you don't need any bits to represent the instances or the class information about the instances in your region, because you anyway know it's class 2. Right? So if you have here like your region again, right, and these are all blue, you don't have to encode for the different instances that they are class blue. You can just essentially externally say this region is blue, and then you need 0 bits, intuitively speaking, to encode this information, right? Because a priori know it's all blue. Again, here you will need to encode, so to say, always 2 bits, which kind of, what is the class of the sample. So a bit more technically, you have to think about like when you randomly draw something from this region, right? You have this region, you randomly pick an instance, and you want to tell, or I want to tell you what is the color of this instance. Here we need 2 bits to encode this information. Here I don't have to tell you anything because you anyway know it's already blue. Okay. So you see, high entropy means flat histogram, means the sampled values are less predictable, which is bad. Or lower entropy means peaky histograms, means it's more predictable. And this predictable we want, right? Because we want to predict in this region, we want to predict what is the class label. And here we have a perfect prediction. And this is why this entropy is a good measure for measuring purity of these regions. So here, just a small detour to this information theory. I already said it a bit. So let's say you want to encode messages with bits, so to say. And let's say you have 4 messages, right? With specific occurrence probabilities, which corresponds to like the class distribution in a specific region. So let's say you have these messages, there's free beer, you have an exam, you have a lecture, nothing is happening. Then these are the likelihoods or the probabilities that you will say the sentence, so to say, right? You will most likely more often say nothing is happening than there is free beer, unfortunately, right? So these are the probabilities. And with information theory, we can more or less encode, or we can find an optimal encoding of this kind of messages, or how we can transmit these messages to some person, right? So meaning if you want to be very efficient in your communication, right, and you don't want to speak out these full sentences, you can think about some binary code to transmit these sentences, right? You could say, for example, every time when I want to say this here, I'm only saying 0. I'm transmitting 1 bit, so to say. If I want to say this here, I'm transmitting 1 0, so 2 bits. If I want to say this or this, I'm using 3 bits here, okay? So the point I want to make here is, it's not always the best to encode your messages in the standard way how you would think about as a computer scientist, that you always use like 2 bits, right? Because naively you could say, okay, if I want to say this sentence, I say 0 0, this sentence means 0 1, and the other sentence means this here, right? This would be like the naive encoding you would do for these 4 sentences, because then you have like these 4 possible choices. Here you don't take the occurrence into account, right? Because you know that this happens so often, it might be more useful to use the code 0 for this, only 1 bit. However, these 2, they occur less often. So instead of just using 2 bits for them, I'm actually using 3 bits, right? And now we can actually see whether this makes any sense. So we could, for example, compute the average number of bits we now need. Okay, so for example, so these 3 bits, I need 1% of the time. 3 bits, 1% of the time. These 3 bits, I need 2% of the time. That's here. These 2 bits, I need 30% of the time. And these 1 bit, I need 67% of the time. And if we compute this average, in average you now need only 1.36 bits. Right? So if you want to say something, in average, you have to say only 1.36 numbers, so to say, right? 1, 0, 0, 0, right? So this is a much smaller number now, of course, than this here, because if you would use this naive encoding, you always need 2 bits, so the average would also be 2 bits. And this essentially what we did here, or this code here is called the Huffman code, or in general, it's like relating to the field of information theory. It tells us how much information also, so to say, is contained, so to say, in this probability distribution. And again, you see for a very clean, pure region, we would, for example, have here 100%. And of course, then we don't need any bit at all, because the rest is already excluded automatically. Okay, so this just is a small detour that you get some feeling that this actually also practically makes sense. You can use it for compression, for example, right? So if you want to now compress a text where always these 3 sentences occur at various positions, right, then you can compress it with this alphabet, so to say, right? And this leads to very good compression here. Good. So then quickly to the other notion, the other measure, so to say, which was the Gini index. And the Gini index can be written in such a way as we see it here, right? It was the probability of picking an event times the probability that it's misclassified. I actually first want to rewrite it that we get a better understanding what this actually is doing. So if you want to rewrite it, you can also write it as this here, minus pi c squared, right? Which is of course the same, and this is what we had at the beginning, so that you don't get confused what we had written here. Right, so here we had 1 minus the squared probabilities, which just comes from the fact when you open up this product, right? So the first one is this, and then the second one becomes this. And since the probability summed up over all classes has to be 1, right? This can be simplified, so it's 1 minus the squared probabilities. So why is this reformulation here on the left-hand side, however, helpful? You can think about it in the following way. So let's say you have again this region, okay? And you have, let's say, 2 blue and 1 red. Oops, and now it's 3 blue and 1 red. So what is this measuring here? So first of all, let's say, let's do the following thought experiment. You randomly pick one of these elements, okay? This is encoded by this probability, okay? So you randomly pick an element, and here you pick randomly, for example, with 3/4 a blue element, and then with 1/4 the other element, okay? So this gives you the probability of picking, so to say, a blue element, right? And then 1 minus this term is a probability that this instance is misclassified, right? Because for the region, you would say it's 1/4 red and 3/4 blue. So if you do like a probabilistic classification, in 1 out of 4 cases you would predict it as red, and in 3 cases you would predict it as blue. So this is the misclassification probability. So one more time. So with this probability you pick a blue instance, and with this probability you say this blue instance is actually red, right? So 1 minus the own probability. Or equivalently, because you have here sum over all classes, with 1/4 probability you pick a red element, and then with 3/4 probability you say this red element is actually blue. Okay, so this is the error. And this is indeed what the Gini index is measuring. Measuring how likely do you pick an element from a class, and then how likely is it misclassified, and then summed up over all classes. Okay, so that's the core idea of this measure, why it actually also makes sense. So as you have already seen in the previous diagram, right, these entropy and the Gini index, more or less both have very, very similar curves. And indeed, in practice, it doesn't really matter too much. There are some theoretical comparisons. In practice, there's not much of a difference. So I would say in practice, you should go with the Gini index for one very subtle reason, that you don't have to compute a log, right? In the entropy, you have to compute a logarithm, which is slightly more expensive than just computing a power of 2, right? So the Gini index is slightly more efficient to compute, which might make a difference at the end of the day. Okay, so but long story short, instead of using misclassification rate, you should use Gini index or entropy as a purity measure, and then you can build your decision tree top down in this greedy fashion. Okay, so here one more time to make this crystal clear, an example. So if you now want to, for example, compute like the Gini index, so this is also please what you should do at home to calculate it. So here's the example. So let's say you have 300 instances at the beginning, which is here the distribution. So mainly blue, a bit green, and a bit red, right? So that's your setting. So you can first compute here this already the delta gain actually. Wait a second, no, this is the Gini index, sorry. So you see that the Gini index was 1 minus the squared proportions, right? So it's 1 minus 67 divided by 300, 65 divided by 300, and 168 divided by 300. Everything is squared. So this gives you a Gini index of 0.5896 apparently for this root node. And if you split, for example, at the position 3 at feature 2, you get these nodes here, which are smaller in size, of course, right? You have subdivided your data, and you don't see the actual numbers. That's not too important, but they would have a Gini index of these corresponding terms. So if you would now compute the gain in the split, right? So here delta is the gain, here's the split. You would see it's like this term minus the size of the left child times the value, right? So this here, this value here, the left child, and this value is this value here of the right child, and these are the corresponding sizes of the child nodes. Then you would see a gain of 0.07. Okay, and as a homework, you should also compute this for the entropy, and you should compute this as well for the misclassification error. So this is simply how it works. Actually, this delta computation is agnostic to the measure. You just have to pick the measure you want to use. And here again are the relative sizes of the child nodes. And then once you have done this, this is a slide I've already shown you to you before, you can do this optimal choice, so to say. You compute this gain for every feature and potentially for every possible threshold. You do it also for the other feature, and you pick the best among these, and you split here, and you recursively continue. And that's essentially the default how you construct a decision tree in a greedy fashion. Good. So let's look at this. Actually, how does it look like? So here, this is what we have seen so far. So the first split would most likely be here. That would be a decision tree of depth 1, so one question, so to say. Then if we continue, we would see that the upper part would split here and the lower part would split here, for example, depth 2. Here we would have the depth 3 again. So we have here in the upper part here this additional split. This here would split here actually, right? You see the tiny split. This here would split here, and so on and so forth. And you can, of course, now continue depth 4 and until you reach perfect purity, right? So that would be the naive idea. You continue, you split, you split, you split, until you reach a state where every region is clean. And this is what we reach here, for example. Now you see really all these nice regions are perfectly clean, only red, only blue, only green. But I guess all of you should now already notice something, that this is not a good idea, right? Again, you have these tiny regions now here, right? So here, this was this green instances, and here's another green instance. So you get all these small stripes, and even here this red one will be a very tiny region you even don't see on the slide. So if you want to achieve perfect accuracy on the training data, this is rarely a good idea, right? Because you have all these fine-grained regions again. It's similar like in a KNN 1NN classifier, but now to a different sense, that you have done too much, so to say, on your training data. You have to make it too fine-grained, so to say. And this problem, indeed, is a problem for the generalization again, right? Big picture, machine learning, we want to find a function which generalizes to unseen data. At least in the supervised learning scenario, we want to generalize to unseen data. But these fine-grained regions are, of course, not good for generalization, right? Because why should an instance which is here be all of a sudden a red instance? This doesn't make any sense, okay? And what is actually the problem here? The problem which we have seen in this model construction now is known as an overfitting problem. Overfitting means that we are doing a very good job on the training data. Right here on the training data, we have 100% purity. Every region is pure, right? In every region, we have only training instances which are class red, for example, right? So here, for example, we have this class red instance. So on the training data, we have 100% accuracy. But if we would apply it to some other data, the validation data, for example, we don't see this, okay? And this is known as overfitting. Overfitting means we model perfectly the training data, or too good the training data, but it does not generalize to other new data. Okay, that's a very important term you should be aware of, overfitting. Okay, and here you see it in more detail again, right? You have low error on the training, but the validation error is comparably high. And actually you can see it, for example, in a nice diagram. So here, for example, we plot the number of leaf nodes. And you can do the same for the K and KNN or some other kind of parameters of your models. So here we measured in the number of leaf nodes, for example. And what you would see is that on your training data, right, that's the data where you decide how to split, right? Remember these three splits again, train, validation, test. On the training data, the accuracy goes up and up and up, of course, right? Because the regions are getting more pure and pure and pure. This is what we do by this greedy heuristic. Until we reach a state where the regions are perfectly pure, then we have this 100% accuracy, right? Training data goes up all the time. However, on the validation data, the data you took aside, you see also first an increase, right? But then at some point you see a drop. Because the model is getting too fine-grained, you have these small regions, and then you don't generalize anymore, so you see a drop, okay? And this is a general behavior, what you often see in machine learning models. The training data should actually always go up, otherwise you're making some mistakes. And the validation data first goes up and then drops at some point, okay? So by the way, 1 or 2 points I want to mention here. So this region here at the beginning, this is the underfitting region. So to say the model is still too simple. Okay, the model class you have picked is too simple. So a tree with only, 5 leaves, meaning a tree with 1 or 2 levels, might not be good enough. It's too simple to explain your data, which is underfitting. And you see that both the training data and the validation data are not good. Okay, so the model is too simple here. Here the model is too complex because you have good performance on training and bad performance on validation. And as you can imagine, what should you do? You should pick a model which is somewhere here, for example, right? Because here the training as well as the validation results are good. So this would be the model you would pick if you have to decide on the depth of the tree, for example. So these are the 2 concepts you should for sure remember, because they will show up later on again. And these plots here, you should always do when doing machine learning research. You should monitor your performance, or later on we see the notion of loss function. You should monitor your loss function on the training data and on the validation data and how they behave with respect to each other. This is a very important concept in machine learning, and it makes sure that you're really picking the right model and that your model is correctly trained and that you don't have, for example, underfitting. So this view is like the classic view, which is actually mostly established. I want to just give here a small side note. There's a new phenomenon, let's call it, like the double descent phenomenon, where we see essentially that the validation data first increases, then drops like here, and then later on increases. And you often see this for like very powerful complex models like neural networks models, where you have lots of data available. So it goes up and down and then it goes up again a bit. So this phenomenon known as double descent is still not fully understood. This is really under active research. I just wanted to mention it here that you have heard about this term, and it might be that in a couple of years we have a much better understanding. So far, you should for sure be familiar with this classic scenario where we have underfitting and overfitting, where this performance decreases. Okay. Good. So with this, I guess it's time to take a short break. And after the break, we will continue a bit more on this topic of evaluation and on these kind of properties of models and how to do this properly. But let's take a short break here.